Okay, now let's transition to the topic Rutherford scattering and nuclear radius. I'm not really sure if this is important or not in your syllabus, but just for the fun of it, let's go through it. Now, formula of nuclear radius. Well, here it is. Okay, R is the radius of atom, and RO is the Fermi radius, which is another constant, and this is the value measured in meters. A is the mass number of the nucleus of the atom. Okay, now the formulas of nuclear density. Okay, now I'm just going to give you a heads up. This isn't important at all. It isn't necessary to memorize this, as later onwards I'm going to mention something extremely important to remember, and it kind of renders this completely useless unless this is required in your syllabus. So this is a formula. This is another one, times by A, only true when the nucleus is spherical. Okay, now this is a way of calculating the mass of the nucleus, where U is the atomic mass unit and this is the constant. Now the relationship between nuclear volume and the mass of the nucleus is that there is just a positive relationship. So as volume increases, mass of the nucleus increases as well. Similar to this, energy of a photon and wavelength. This is nuclear density, another formula that you may or may not have to memorize depending on your syllabus. The relationship between the density of the nucleus is the same for all nuclei. And now, here's where I bring up the same point I was talking about over here regarding whether or not this might even be useful for you. So it's the same for all nuclei, as in it's constant. It's the same value for every single atom. And when I mean every single atom, I mean every single atom when it comes to the density of the nucleus. And it's independent of the nuclei, as all variables are constant in the formula above. So pi is constant, U is constant, and so is RO. Fermi radius. This is the value, U has this value, and then pi, it is either 22/7 or 3.14. Nuclear density is always in the order of 10 to the power of negative 17. And what I mean by it's always in the order, there's only one order because there's one value of nuclear density for every single nuclei. So 10 to the power of negative 17 is constant throughout. Now this is the observation of the nuclear density. It's significantly larger than the atomic density, which suggests the following. Majority of the atom is contained in the nucleus itself. Nucleus is quite small compared to the entire atom, and atoms are predominantly comprised of space, as stated previously. Now, the point of closest approach. Well, this is quite a fascinating topic, and it might interest you, or might not, but let's get on with it. Okay, this is a definition. It's where the speed of the alpha particles becomes momentarily zero due to repulsive force. Okay, an account of observations made from the Rutherford experiment. Some of the alpha particles were found to come straight back, as we stated over here. Let me just pull it up. Yep, here. The alpha particles just went straight past, and that's pretty much it. It didn't even interact with the nucleus like these ones, less than 10 degrees and greater than 90 degrees. Now, this indicated that there is electrostatic repulsion between the alpha particles as well as gold nucleus. Here's an example of alpha particles traveling towards the gold foil. As it moves closer and closer to the gold foil, electric potential energy is transferred into initial kinetic energy. The alpha particle arrives at a point called distance of closest approach where the two, initial kinetic energy and electric potential energy, is equal to one another due to the conservation of energy, where energy is neither created nor destroyed. And in this case, electrical potential energy is transferred into kinetic energy, which preserves the statement by conserving the energy through the transfer of the two. The formula of electric potential energy is this, where K is the Coulomb's constant, 8.99 into 10 to the power of 9. The capitalized Q is 2e, the charge of alpha particles in this scenario. Q is Z into E, the charge of target nucleus, which is this. When you plug all of the values in, you get the following formula, specifically tailored towards alpha particles traveling towards the gold foil. And when you rearrange the formula, you get this to calculate the distance of closest approach, otherwise known as R. And this is where, as said before, due to the conservation of energy, kinetic energy is equal to electric potential energy. Now, the deviations from Rutherford scattering. The previous assumption was that alpha particles only interact through electrostatic repulsion. However, there is an exception. When alpha particles exceed 27.5 mega electron volts, it'll be close enough to interact with the nucleus by means of strong nuclear force. These are the expected results from the Rutherford formula, as represented by this red line. However, if the alpha particle is able to acquire an energy of 27.5 mega electron volts, it ends up here. So this is an experimental observation, and let's move on to the graphical analysis. Now you can analyze this graph. There's repulsive, attractive, electric repulsion between protons, strong nuclear force between nucleons over here. Strong nuclear force dominates the separation. And yeah, that's pretty much it. You might not be able to see all of the labels over here in both of these graphs clearly. Some of them are cut off. So we'll be providing a link to all of these slides in the chat below.